the nature of space and its endless expansion. Let's begin with a moment of stillness. On a moonless night, when the city has fallen asleep and light pollution recedes to the horizon, look up at the sky. What you see are not just shimmering specks on a canvas of infinite black. You are gazing into the depths of time, into the oldest stories ever told in the language of light. Each star is a distant sun, each galaxy an archipelago of billions of suns, and between them lies a void that seems empty, silent, and eternal. But within that profound silence, one of the most astonishing truths about reality is quietly unfolding. The universe is expanding. The space between galaxies is not a static stage where actors move. It is a fabric that is being stretched. Every galaxy is moving away from every other galaxy, not because they are flying apart, but because the very space between them is being created anew, second by second, minute by minute. Upon hearing this, the human brain, evolved to survive in a finite world with familiar rules, immediately poses what seems like an eminently logical question. If the universe is expanding, what is it expanding into? This question, simple in its phrasing, is a doorway to one of the deepest chasms of perception. It exposes the profound limits of human intuition and forces us to confront a reality far stranger than any science fiction tale. Because the answer, both bewildering and liberating, is, it isn't expanding into anything. In this article, we will begin a journey to dismantle this trap of intuition, to understand why the question "into what" is the wrong question to ask. We will explore the true nature of space, not as a container that holds everything, but as the very fabric of existence itself. We will delve into Einstein's concept of space-time, where space and time are inseparable and together they bend, stretch, and ripple in the cosmic dance. This is the first chapter in understanding the cosmos, a chapter that requires us to abandon our most familiar assumptions to behold a grander picture, a reality where an outside may not exist at all. Human thought is a phenomenal survival tool, honed over millions of years of evolution to navigate a specific environment, the surface of a rocky planet orbiting an average star. All our concepts are built upon experiences in this three-dimensional world. We understand inside and outside, up and down, beginning and end. An object always exists within a larger space. An apple rests on a table, the table is in a room, the room is in a house, and so on. When we think of expansion, our brain immediately retrieves familiar analogies. The first and most common is a balloon. When you inflate it, its rubber surface swells, growing larger. The balloon is expanding. And what is it expanding into? Into the air around it. It occupies a space that was already there. This expansion is visible, measurable, and perfectly aligns with our intuition. It has an inside, the air you blew in, and an outside, the room. Or consider a drop of ink falling into a glass of water. The ink spreads, diffuses, and expands into the clear volume of water. Again, there is a clear boundary, something spreading into something else. These very metaphors, so useful in daily life, become a conceptual cage when we confront the universe. When astronomers announce that the universe is expanding, we automatically apply the balloon model. We envision the cosmos as a giant bubble inflating within some vast, empty void. And so the question "into what" arises naturally. If there's a balloon, there must be air around it. If there's a universe, there must be a superspace outside of it. This is precisely the trap. The universe, according to all that modern science understands, is not an object in space. The universe is space. There is no air outside the universe. There is no place for it to expand into. The concept of outside the universe is a contradiction in terms because outside is itself a spatial concept. If an outside existed, by definition, it would also be part of the universe. To escape this trap, we must make a cognitive leap. We must abandon the notion of space as a static stage. Instead, we must learn to see space as a dynamic, flexible entity that can be created, warped, and stretched. Albert Einstein was the first to guide us down this path. He showed that space is not emptiness but a structure, a fabric that can be influenced by matter and energy. And it is this fabric, the entire fabric, that is stretching. The expansion isn't happening at some edge, conquering new territory. It is happening everywhere, all at once. The distance between two distant galaxies increases not because they are flying through space, but because the very space between them is being born. Let's try another analogy, still flawed but closer to the truth. Imagine the surface of a loaf of raisin bread rising in an oven. You are an ant living on one of the raisins. As the bread rises, you see all the other raisins moving away from you. The raisins farther away appear to recede faster. You get the sense that you are the center of this expansion. But if you were to jump to another raisin, you would observe the exact same thing. Every raisin sees itself as the center. In this scenario, there is no true center. The dough is rising everywhere. And most importantly, the dough is not expanding into anything else. It is simply puffing up on its own. Now, elevate this analogy to 3 dimensions, replace the dough with space, and the raisins with galaxies. That is the closest picture we can get of the universe's expansion. There is no edge, no center, and no outside. The question expanding into what becomes meaningless, much like asking what is north of the North Pole. The concept of north exists only on the surface of the Earth and loses its meaning at the pole itself. Similarly, the concept of outside loses its meaning when we talk about the entirety of space. Accepting this requires intellectual humility. It requires us to acknowledge that our brains, however magnificent, have limits shaped by our evolutionary experience. The universe is under no obligation to conform to human intuition. And only when we overcome these cognitive barriers can we begin to appreciate the true beauty of a self-contained, self-creating, and self-expanding cosmos. Before Albert Einstein, the world of physics was dominated by the vision of Isaac Newton. In Newton's universe, space was an absolute, 3-dimensional, unchanging stage. It was like a giant, invisible coordinate system where planets, stars, and all other objects moved. Time was also absolute, a universal river flowing at the same steady pace for everyone, everywhere. Space and time were separate entities, providing the backdrop for the cosmic drama. But in the early 20th century, Einstein ignited a revolution that shook the very foundations of physics. Beginning with his special theory of relativity, 1905, he demonstrated that space and time are not absolute. The passage of time and the measurement of space depend on the relative motion of the observer. The only universal constant, the cosmic speed limit, is the speed of light in a vacuum. This led to a stunning conclusion. Space and time are inseparable. They are woven together into a single 4-dimensional construct known as spacetime. Imagine a stretched rubber sheet. This is a 2-dimensional analogy for spacetime. If you place nothing on it, the sheet remains flat. A marble rolling across this flat sheet will travel in a straight line. This is the Newtonian view of the universe. But with his general theory of relativity, 1915, Einstein went even further. He proposed that the presence of matter and energy warps this fabric of spacetime. Place a heavy bowling ball in the center of the rubber sheet. The sheet will sag. Now, if you roll a small marble near the bowling ball, it will no longer travel in a straight line. It will be drawn into the depression, following a curved path around the indentation. To us, observing from the outside, it appears as though some invisible force, gravity, is pulling the marble toward the bowling ball. But from the marble's own perspective, it is simply following the straightest possible path on a curved surface. This is the essence of gravity according to Einstein. Gravity is not a mysterious force between objects. It is the geometric consequence of the curvature of spacetime. The Earth orbits the Sun not because the Sun pulls it, but because the Sun's immense mass creates a deep well in spacetime, and the Earth is following a natural straight path, a geodesic, within that well. Light, which has no mass, must also follow these curves. This is why light from distant stars bends as it passes near massive objects like the Sun. A prediction of Einstein's that was experimentally verified, turning him into a global icon. So, what does this have to do with the expansion of the universe? Everything. If spacetime is a flexible fabric that can be bent by matter, then it can also have its own dynamic properties. It doesn't have to be static. Einstein's field equations, when applied to the universe as a whole, naturally predicted that this fabric must either be expanding or contracting. A static universe was an unstable state. When we say the universe is expanding, what we are really saying is the fabric of spacetime is being stretched. This stretching doesn't just affect space. Since time is an inextricable part of the fabric, it is affected too. As space expands, time also dilates. This means that the rhythm of time in a very distant galaxy, where space is expanding rapidly relative to us, will appear to run slower from our perspective. The light from distant supernovae is not only redshifted, its wavelength is stretched out. But the entire event of the star brightening and fading also takes longer than it would for a similar explosion nearby. We are watching a slow-motion movie of the cosmos, a direct consequence of spacetime itself expanding. This concept completely resolves the expanding into what? Paradox. The fabric of spacetime is not located in some other space that it can expand into. It is the entire structure of reality, contains itself. The expansion is an intrinsic property of the fabric, just as elasticity is a property of rubber. It doesn't need an outside to manifest that property. Understanding that we live on a dynamic 4D fabric, not in a static 3D box, is the most crucial turning point in grasping modern cosmology. It allows us to envision a universe that is finite yet has no boundary, just as the 2D surface of a sphere is finite but has no edge, or a universe that is infinite and still expanding. An infinite sheet can be stretched so that the distance between points on it increases, while it remains infinite. In both scenarios, the question "what's outside?" is moot. For the finite, unbounded universe, there is no outside to travel to. For the infinite universe, outside is a meaningless concept. All that is, all space and all time is part of this single fabric. And that fabric, our reality, is in a state of constant transformation, a process we call expansion. Once we accept that space itself is expanding, another intuition-driven question arises. If there's an expansion, wasn't there a starting point, a center of the explosion? This is yet another legacy of familiar metaphors. When a bomb detonates, shrapnel flies outward from a central point. We can trace the trajectories back to find ground zero. So, when we hear about the Big Bang, we tend to picture a point in empty space that exploded, with galaxies being the fragments flying away from that single location. According to this mental model, there must be a special place in the universe, the center of it all. And if we looked far enough, we would see the galaxies at the edge of the explosion, and beyond that, the empty space the explosion has yet to reach. But this model is completely wrong. The Big Bang was not an explosion in space. It was the beginning of space and time itself. It did not happen at a particular point. It happened everywhere at once. To understand this, let's return to the rubber sheet analogy. Imagine you draw countless dots on an unstretched sheet. These dots represent galaxies. The Big Bang corresponds to the moment the sheet begins to be stretched in all directions. What happens? Every dot moves away from every other dot. If you are standing on any given dot, you will see all the other dots receding from you. The dots farther away will seem to recede faster, because there is more fabric between you and them being stretched. This creates the illusion that you are at the center of the expansion. But here is the crucial part. This illusion is true for every single dot. Every observer in every galaxy will perceive themselves to be at the center of an expanding universe. This is a profound consequence of the cosmological principle. On a large scale, the universe is homogeneous, the same everywhere, and isotropic, the same in every direction. There is no privileged location, no special direction. The universe has no center, just as the surface of a sphere has no starting or ending point. So, if the Big Bang was not a point in space, what was it? It was a moment in time. It was the moment in the distant past when our entire observable universe was compressed into an unimaginably hot and dense state. From that moment, space itself began to expand. The space you are in right now, the space in your room, the space between the Earth and the Moon, all of it is part of the expansion that originated from that instant. This means the Big Bang didn't happen over there in some distant corner of the cosmos. It happened right here where you are sitting. It also happened in the Andromeda Galaxy. It happened in the most distant galaxies the James Webb Space Telescope can see. The entire universe is the legacy of that initial moment. This understanding frees us from the search for a geographical location of creation. Our origin is not a place, but a state of near-infinite density and energy, from which the space-time we know unfurled and began its 13.8 billion-year journey. When we look at the cosmic microwave background, CMB, the afterglow of light from that early era, we see it coming from every direction in the sky with an almost perfectly uniform temperature. This is the most powerful evidence that the Big Bang happened everywhere. If it were an explosion from a single point, we would only see the residual heat from one particular direction. But no, we are bathed in the light of our own cosmic dawn. We are living inside the remnants of creation. Therefore, the expansion of the universe is not the movement of matter away from a center. It is the relative increase in distance between objects. The Earth is not being pushed away. The Andromeda Galaxy is not either. But the space between us and a galaxy 10 billion light-years away is being stretched at an enormous rate, causing that distance to grow continuously. This expansion, occurring within itself and without a center, is one of the most beautiful and profound concepts in cosmology. It places every location in the universe, including our tiny Earth, on an equal footing. We are not the center, but we are not at the edge either. We are simply part of a magnificent whole, a cosmic tapestry that weaves itself, expanding not to conquer something else, but simply to become more fully itself. We started with a simple question: what is the universe expanding into? And the journey for an answer has led us through ideas that completely reshape our view of reality. We have seen that the question itself stems from an intuitive trap, an attempt to impose the rules of a finite world onto something that may be infinite. We have learned that the universe is not an object existing in space, but rather that it is space-time. Thanks to Einstein's revolution, we know that space and time are not a static stage but a single, dynamic 4D fabric that can be warped by matter and can expand on its own. This expansion has no center. It happens everywhere, causing every galaxy to recede from every other. Thus, the answer to our initial question is not a place or another dimension, but a conceptual shift. The universe expands into nothing. It expands within itself. It is a closed, self-contained system. It generates its own space to exist in. This might leave us feeling small and a bit dizzy. A reality with no outside seems to challenge our basic human need for orientation and boundaries. But at the same time, it offers a deep sense of connection. The space in your breath, the space separating you from this screen, is the same space that is expanding between the galaxies. We are all part of the same dynamic process, a creative event that has lasted 13.8 billion years and is still ongoing. We have not answered all the questions. What is the evidence for this expansion? What is driving it? And where will it lead? These will be the topics for the articles to come. But here, at this first resting point, we have achieved something crucial. We have learned to ask the right questions. Instead of asking into what, perhaps the more profound question is, how can a reality exist and expand on its own, needing nothing but itself? In that question lies not confusion, but the beginning of awe and wonder. The echoes of creation, evidence for a growing universe. In the previous article, we undertook a revolution in perception. We abandoned the image of the universe as a balloon inflating in an empty room and instead learned to envision it as an infinite fabric of space-time stretching itself. We understood that there is no center, no edge, and no outside. Expansion is an intrinsic property of reality. But an idea, no matter how elegant and logical, must be tested against reality. Science does not operate on faith, but on evidence. So, where is the evidence for such a dynamic, expanding universe? How can tiny beings on a rocky planet measure the breadth of the entire cosmos? The answer, poetically, lies right above our heads. The night sky is not just a window into space. It is a window into the past. Light, despite traveling at the staggering speed of nearly 300,000 kilometers per second, still takes time to cross the immense distances between galaxies. Light from the moon takes over a second to reach us. Light from the sun takes 8 minutes. Light from the next nearest star, Proxima Centauri, takes over 4 years. and the light from the Andromeda Galaxy, our closest major neighbor, began its journey 2.5 million years ago, when the human species had not yet evolved into its current form. This means that the farther we look, the deeper we see into the past. The James Webb Space Telescope can capture images of galaxies that existed over 13 billion years ago, showing us the universe when it was just an infant. The sky is a perfect time machine, and those ancient rays of light are fossils, archaeological artifacts carrying within them the story of creation. In this article, we will decode two of the most important messages the universe has sent us. First, we will listen to the Song of Stretched Light, the phenomenon of cosmological redshift, which is irrefutable proof that space is expanding right now. Then, we will look at the oldest photograph ever taken, the cosmic microwave background, the glowing remnant of the Big Bang itself. Finally, we will discover how tiny wrinkles in that primordial photograph became the seeds for all magnificent structures, from stars and galaxies to our very existence. This is the story of how we know what we know, a story of curiosity, perseverance, and the accidental discoveries that forever changed humanity's place in the cosmos. Let's start with a familiar experience. You are standing by the side of a road, and an ambulance with its siren blaring passes by. As it approaches, the siren's pitch sounds higher. The moment it passes you and starts to move away, the pitch abruptly drops. This phenomenon is called the Doppler effect. It occurs because sound waves are compressed as the source approaches, increasing their frequency, hence a higher pitch, and stretched as the source recedes, decreasing their frequency, hence a lower pitch. Light, being a wave, behaves similarly. If a star is moving towards Earth, its light waves get compressed, shifting towards the shorter wavelength end of the spectrum, the blue end. We call this blue shift. Conversely, if a star is moving away from us, its light waves get stretched, shifting towards the longer wavelength end, the red end. This is called redshift. In the 1920s, American astronomer Edwin Hubble spent his nights at the Mount Wilson Observatory, using the most powerful telescope of his time to study faint, fuzzy nebulae in the sky. Back then, it was still debated whether these nebulae were gas clouds within our own Milky Way galaxy or separate island universes, that is, other galaxies. Hubble, building on the work of astronomers like Vesto Slipher, did two extraordinary things. First, by observing special variable stars, called Cepheid variables, he measured the distances to these nebulae and proved conclusively that they were indeed separate galaxies, millions of light-years away. The universe suddenly became vastly larger than anyone had ever imagined. But it was his second discovery that truly rocked the world. When analyzing the light from these galaxies, Hubble found that almost all of them were redshifted. This meant they were moving away from us. More importantly, he discovered a stunning relationship. The farther away a galaxy is, the faster it is moving away. This relationship, now known as the Hubble-Lemaitre law, was the first observational evidence that the universe was not static. It was expanding. However, there is a crucial subtlety here, a distinction that brings us back to the core theme of the previous article. The redshift Hubble observed from very distant galaxies is not entirely like the sound of the ambulance siren. It is not primarily caused by galaxies flying through static space. Instead, it is the result of space itself expanding between us and that galaxy while the light is in transit. This is called cosmological redshift. Imagine a photon of light as a small wave traveling on the surface of the spacetime fabric. As the photon begins its billion-year journey from a distant galaxy, the spacetime fabric it is traversing is constantly being stretched. The light wave, being a part of that fabric, gets stretched along with it. Its wavelength increases, and its energy decreases. By the time it finally reaches our telescopes, it has been significantly reddened, not because the galaxy is speeding away at a fantastic velocity, but because the universe has grown immensely during the light's journey. This difference is profound. If galaxies were simply flying apart in a static space, they would be limited by the speed of light. But because space itself is expanding, there is no speed limit to the expansion. For very distant galaxies, the space between us and them can expand faster than the speed of light. This does not violate Einstein's theory of relativity, as no matter is moving through space faster than light. Only space itself is being created faster. The light from such galaxies will never reach us. They are beyond our cosmic horizon, forever separated by an expanding ocean of space. Hubble's law is therefore more than just a graph of velocity versus distance. It is a measure of the expansion of space itself. Each data point on his graph is a note in the song of the universe, a song whose melody is stretched out by time and space. By listening to this redshift, we are not just hearing motion. We are hearing the rhythm of ongoing creation. If the universe is expanding today, then logically it must have been smaller, denser, and hotter in the past. If we rewind the cosmic film, galaxies would get closer, space would shrink, and temperatures would rise. Rewind far enough, about 13.8 billion years, and we arrive at a time when the entire observable universe was compressed into an unimaginably hot and dense state. This is the state we call the Big Bang. This theory, developed in the mid-20th century by physicists like George Gamow, made a bold prediction. If the early universe was truly a brilliant fireball, it must have left behind a thermal afterglow, a residual light that should still be detectable today. Imagine the universe in its first few 100,000 years. It was an utterly alien place. No stars, no planets, no galaxies. It was just a hot, dense plasma soup of fundamental particles. Protons, neutrons, and electrons, all bathed in a sea of high-energy photons, light particles. In this scorching environment, electrons could not combine with atomic nuclei to form stable atoms. They roamed free. The problem was, photons constantly collided with and were scattered by these free electrons. A photon couldn't travel more than a few centimeters without being deflected. As a result, the universe was completely opaque. It was like being in the middle of a thick, glowing fog. You couldn't see through it, but the universe continued to expand and cool. Around 380,000 years after the Big Bang, a critical event occurred. The universe's temperature dropped to about 3,000 Kelvin. At this temperature, electrons were finally cool enough to be captured by protons, forming the first neutral hydrogen atoms. This process is called recombination. As the free electrons were locked up inside atoms, the main obstacle for photons vanished. Suddenly, light could travel freely through space without being scattered. The universe became transparent. This moment is known as decoupling, as matter and radiation ceased their intense interaction. The light released at that moment is the oldest light in the universe. It has been traveling through space for 13.8 billion years, coming at us from every direction in the sky. However, just like the light from distant galaxies, this first light has also been affected by the expansion of the universe. During its long journey, its wavelength has been stretched dramatically by a factor of about 1,100. The high-energy light of a 3,000-degree universe has been redshifted all the way down to the microwave portion of the electromagnetic spectrum. Its corresponding temperature today is a frigid 2.7 Kelvin, or minus 270.45 degrees Celsius. This is the cosmic microwave background, CMB. In 1965, two American radio engineers at Bell Labs, Arno Penzias and Robert Wilson, were working with a large radio antenna. They kept detecting a faint, persistent, hissing noise coming from every direction they pointed the antenna. They tried everything to eliminate it, assuming it was an equipment malfunction or interference from nearby New York City. They even climbed into the antenna to clean out what they described as a white dielectric material, suspecting it was pigeon droppings. But the noise remained. At the same time, a team of physicists at Princeton University, led by Robert Dicke, was preparing to build a device to search for this very thermal remnant of the Big Bang. When Penzias and Wilson learned of the Princeton group's work, they had an epiphany. Their mysterious noise was not noise at all. It was the echo of creation. They had accidentally discovered the CMB. This discovery, which earned them the Nobel Prize in Physics in 1978, is considered the smoking gun for the Big Bang theory. It confirmed that the universe did indeed begin in a hot, dense state and has been cooling due to expansion ever since. Moreover, the fact that the CMB comes from every direction with an almost perfectly uniform temperature powerfully reinforces the cosmological principle. The Big Bang didn't happen at a point, it happened everywhere. We are bathed in the afterglow of our own cosmic dawn. The discovery of the CMB solved one great mystery but raised another. If the early universe and the CMB were so perfectly uniform, then why is the universe today so lumpy? It is not a smooth, evenly distributed gas. It is filled with enormous structures: stars, galaxies, galaxy clusters, and superclusters, separated by vast cosmic voids. Where did all this structure come from? If everything started out perfectly smooth, how did complexity arise? The answer lies in the incredibly fine details of the CMB. While it is almost uniform, subsequent satellites launched to study it in greater detail. COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s detected minuscule temperature fluctuations in the CMB. These are the hot spots and cold spots on the CMB map, with differences of only about 1 part in 100,000. These tiny wrinkles, these subtle imperfections, are the most important things in the entire universe. What are they? They are a snapshot of tiny density fluctuations in the primordial plasma soup, just before the light was released. The cold spots on the CMB map correspond to regions that were slightly denser than average. The hot spots correspond to regions that were slightly less dense. The difference was minuscule, but it was all that was needed. Gravity is a rich-get-richer process. A region that is slightly denser has slightly more gravity. This slightly stronger gravity begins to pull in matter from the surrounding areas. Over time, this makes the region even denser, which makes its gravity even stronger, which in turn pulls in even more matter. This is the mechanism of cosmic structure formation. The tiny density fluctuations in the early universe, frozen into the CMB like fossils, acted as gravitational seeds. Over the following hundreds of millions of years, gravity did its work, slowly amplifying these initial inhomogeneities. Matter, mostly the mysterious dark matter, which we will discuss later, began to clump around these seeds, forming massive dark matter halos. Ordinary gas, like hydrogen and helium, was then pulled into these halos, where it compressed and heated up until nuclear fusion ignited, giving birth to the first stars. These stars then gathered into the first galaxies. Galaxies, in turn, were drawn together to form galaxy clusters. And galaxy clusters arranged themselves into a vast, web-like structure known as the cosmic web, with filaments, walls, and clusters interspersed with giant voids. This entire magnificent cosmic dance, all the complexity of the modern universe, originated from nearly imperceptible quantum wrinkles in the primordial moment. The CMB is not just a photograph of the infant universe. It is the blueprint for the adult universe. It contains the genetic code for everything that was, is, and will be. Every galaxy you see, the star that warms us, and the very atoms in your body can trace their lineage back to a tiny fluctuation in the sea of energy at the dawn of time. In this journey, we have traveled from observing distant galaxies to listening to the faint echo of the Big Bang itself. We have seen the two great pillars of evidence that support the model of a universe expanding from a hot, dense beginning. First is the cosmological redshift, observed by Hubble, which shows that space is stretching right now, carrying galaxies apart and elongating light on its journey. This is the evidence for the universe's present-day dynamism. Second is the cosmic microwave background, accidentally discovered by Penzias and Wilson, which is the afterglow of the primordial fireball. This is the evidence for the universe's hot, dense past. Its tiny fluctuations also explain the origin of all the structures we see today. The astonishing thing is that these two pieces of evidence are not separate stories. They fit together perfectly to form a single, coherent narrative. The expansion Hubble saw is the same expansion that has cooled the fire of the Big Bang into the CMB. The structures seeded by the wrinkles in the CMB are the very galaxies Hubble observed. From the distant past to the present, from the largest scales to the smallest details, the story of an expanding universe is consistent and inescapable. We now know that the universe is expanding, but the story is far from over. Another crucial question arises. How is this expansion proceeding? Is it slowing down under the pull of gravity, as everyone once thought? Or is there something else, some mysterious force, dictating the fate of the cosmos? The answer to this question will lead us into the territory of the greatest mysteries in modern science: dark matter and dark energy. That will be the subject of our next article, where we discover that the universe is not only expanding, but it is doing so at an ever-accelerating rate, driven by the very emptiness of space itself. The unseen architect's dark matter and the accelerating universe. We have journeyed far. We have stood on the shoulders of Einstein to see reality not as a static box but as a dynamic fabric of spacetime. We have listened with Hubble to the stretched song of receding galaxies and peered with Penzias and Wilson into the faint, glowing embers of the Big Bang itself. The evidence is overwhelming. We live in an expanding universe, born from a hot, dense state 13.8 billion years ago. The story seems coherent, elegant, and complete. And yet it is not. For as long as we have understood gravity, one expectation has seemed certain. The cosmic expansion initiated by the Big Bang should be slowing down. Gravity, the universal force of attraction, acts as a cosmic brake. Every star, every galaxy, every cluster pulls on every other, constantly trying to rein in the expansion. For much of the 20th century, the great cosmological debate was not if the expansion was slowing, but by how much. Would gravity be strong enough to eventually halt the expansion and pull everything back together in a fiery big crunch? Or would the expansion slow forever but never quite stop, leading to a cold, dark, big freeze? To answer this, astronomers set out to take a census of the universe, to add up all the matter and energy to see if there was enough gravitational pull to reverse our cosmic fate. But when they began to count, they found something profoundly disturbing. The numbers didn't add up. The universe we could see, the brilliant stars, the glowing nebulae, the majestic spiral galaxies, was only a tiny fraction of what needed to be there. An invisible majority was hiding in the shadows, its gravitational influence shaping the cosmos in ways we were only just beginning to detect. This article is the story of that cosmic census and the shocking discoveries it revealed. It is a journey into the dark side of the universe. We will first encounter dark matter, the invisible scaffolding upon which all cosmic structures are built, a mysterious substance whose gravity holds galaxies together. Then, we will confront an even deeper enigma: dark energy, a repulsive force woven into the fabric of space itself, a force that has overridden gravity and is pushing the universe apart at an ever-accelerating rate. This is the story of how we realize that everything we can see, everything we have ever known, is merely the foam on the crest of a deep, dark, cosmic ocean. We are about to discover that 95% of our universe is composed of ingredients unknown to science, unseen architects that govern the birth, life, and ultimate death of reality itself. Our first clue that the universe was hiding something came not from looking at its expansion, but from watching things spin. In the 1930s, the brilliant and eccentric Swiss-American astronomer Fritz Zwicky was studying the Coma Cluster, a colossal swarm of over 1,000 galaxies bound together by gravity. By measuring the Doppler shift of the light from these galaxies, he could calculate how fast they were moving. What he found was baffling. The galaxies within the cluster were moving at tremendous speeds, far too fast for the cluster's gravity to hold them together. Based on the amount of visible matter, the stars within the galaxies, the gravitational pull should have been far too weak. The cluster should have long since flown apart, its member galaxies dispersing into the void. To explain why it remained bound, Zwicky postulated the existence of a huge amount of unseen matter, which he termed dunkle materie, dark matter. This invisible mass, he proposed, provided the extra gravitational glue needed to keep the cluster intact. Zwicky's idea was so radical for its time that it was largely ignored for decades. The case for dark matter was resurrected and made undeniable in the 1970s, thanks to the meticulous work of astronomer Vera Rubin. Instead of looking at clusters of galaxies, Rubin studied the rotation of individual spiral galaxies, including our own neighbor Andromeda. According to Newton's laws of gravity, which work perfectly in our solar system, objects farther from the center should orbit more slowly. Mercury, the closest planet, zips around the Sun, while distant Neptune plods along at a much slower pace. The same should be true for stars in a galaxy. Stars near the bright, dense center should move quickly, while stars at the dim, sparse outer edges should move much more slowly. Vera Rubin and her colleague Kent Ford developed new, highly sensitive instruments to measure the speeds of stars and gas clouds at various distances from their galactic centers. Night after night, they collected data, expecting to see the orbital speeds drop off as they looked farther out. But they didn't. In galaxy after galaxy, they found the same shocking result. The stars at the very edge were moving just as fast as the stars near the center. This flat rotation curve was a flagrant violation of the laws of gravity, unless the galaxies contained far more mass than could be seen. It was as if our entire solar system, from Mercury to Neptune, was embedded in a giant, invisible sphere of matter, causing all the planets to orbit at the same speed. Rubin's data was the smoking gun. The conclusion was inescapable. Galaxies are not just the islands of light we see. They are embedded within vast, spherical halos of dark matter, extending far beyond their visible edges. The visible galaxy is like the tip of an iceberg. The vast majority of its mass is submerged and invisible. So what is this dark matter? The first and most obvious guess was that it's just ordinary matter that doesn't shine. This could include things like cold gas, dust, brown dwarfs, failed stars, neutron stars, and black holes. Astronomers grouped these potential candidates under the acronym MACHOs, massive compact halo objects. For a while, this seemed like a plausible solution. But extensive searches, using techniques like gravitational lensing, where a massive object bends the light of a star behind it, found far too few MACHOs to account for the missing mass. Furthermore, our understanding of the early universe, specifically the process of Big Bang nucleosynthesis, the formation of the first light elements, places strict limits on the total amount of normal, baryonic matter that can exist. The observed abundances of hydrogen, helium, and lithium in the cosmos match the predictions perfectly, but only if normal matter makes up just about 5% of the total cosmic density. Dark matter, on the other hand, appears to make up about 27%. This means that the vast majority of dark matter cannot be made of the same stuff as us: protons, neutrons, and electrons. It must be something fundamentally new. This has led physicists to propose that dark matter is composed of a new type of subatomic particle, one not included in the standard model of particle physics. The leading candidates are called WIMPs, weakly interacting massive particles. As their name suggests, these hypothetical particles are massive, providing the gravity. But they are weakly interacting, meaning they barely notice normal matter. They don't interact with light, making them dark. Nor do they interact through the strong nuclear force or electromagnetism. They pass through us, the Earth, and everything else as if we were ghosts. Their existence is only revealed through their collective gravitational pull. All around the world, deep underground and shielded laboratories, scientists are running complex experiments trying to catch a fleeting glimpse of a WIMP bouncing off an atomic nucleus, a discovery that would undoubtedly earn another Nobel Prize. Regardless of its true identity, the role of dark matter in the cosmos is absolutely crucial. It is not just some passive, space-filling substance. Dark matter is the scaffolding of the universe. As we learned in the previous article, the structures we see today grew from tiny density fluctuations in the early universe. It was the immense gravity of dark matter that acted first, clumping together around those initial seeds. These dark matter halos then acted as gravitational wells, pulling in the ordinary gas that would eventually cool, condense, and form the stars and galaxies we see. Without dark matter, gravity would have been too weak to form structures as quickly and as large as we observe. The beautiful cosmic web, with its filaments and voids, is primarily a map of the underlying dark matter distribution. Dark matter is the unseen architect of our cosmic home. With the existence of dark matter established, the cosmic census seemed more complete. Astronomers now had a better handle on the total amount of mass in the universe. The new inventory consisted of about 5% normal matter and 27% dark matter. Adding it all up, cosmologists calculated that this was still not enough gravity to halt the expansion and cause a big crunch. The prevailing view in the 1990s was that we were destined for a big freeze, an eternal expansion that would gradually slow down over trillions of years but never stop. The only remaining task was to measure the rate of this deceleration. To do this, two independent teams of astronomers embarked on one of the most ambitious observational projects ever undertaken. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their strategy was to use a specific type of stellar explosion, a Type Ia supernova, as a cosmic measuring stick. Type Ia supernovae are special. They occur when a white dwarf star, the dead, compact remnant of a star like our Sun, in a binary system siphons off too much matter from its companion. When its mass reaches a precise critical limit, about 1.4 times the mass of our Sun, it triggers a runaway thermonuclear explosion that tears the star apart. Because they all explode at the same critical mass, they all have roughly the same intrinsic brightness. They are standard candles. This property is incredibly useful. If you know how bright something truly is, you can determine its distance by measuring how bright it appears to be. A distant streetlight appears dimmer than a nearby one. By comparing the apparent brightness of distant Type Ia supernovae to their redshift, which measures how much the universe has expanded since they exploded, the teams could reconstruct the expansion history of the universe. They were essentially looking back in time to see if the universe was expanding faster or slower in the past. Everyone expected to find that the supernovae were brighter than expected for their redshift, which would indicate that the expansion was faster in the past and has been slowing down. In 1998, both teams announced their results, and the world of physics was turned upside down. The most distant supernovae were not brighter than expected. They were dimmer. They were farther away than they should have been. This was a bombshell. The only way for them to be farther away was if the expansion of the universe had not been slowing down at all. Instead, for the last 5 to 6 billion years, it has been speeding up. The universe was not just expanding, it was accelerating. Gravity was not winning the cosmic tug-of-war. Something else, some mysterious, repulsive force, was pushing everything apart. The discovery was so profound and unexpected that it was awarded the 2011 Nobel Prize in Physics. This something was given a name as enigmatic as its nature: dark energy. The discovery of cosmic acceleration presented an even greater puzzle than dark matter. While dark matter is a strange substance, it at least behaves gravitationally as we'd expect matter to. It clumps and attracts. Dark energy does the opposite. It is a smooth, diffuse component of the universe that acts as a form of anti-gravity, pushing space-time apart. What could it possibly be? The leading and simplest explanation is an idea that goes all the way back to Einstein, the cosmological constant, represented by the Greek letter lambda. As you may recall, Einstein originally introduced this term into his equations to force a static universe, a decision he later called his biggest blunder. But in a stunning twist of fate, his blunder has returned as the most plausible candidate for dark energy. In modern physics, the cosmological constant represents the energy of empty space itself, the energy of the vacuum. According to quantum mechanics, a vacuum is not truly empty. It is a seething cauldron of virtual particles that pop in and out of existence in fleeting moments. This quantum phys endows every cubic centimeter of space with a fundamental intrinsic energy. And according to general relativity, this vacuum energy would exert a negative pressure, causing space to expand. This explains the acceleration perfectly. As the universe expands, the density of matter, both normal and dark, decreases because it gets spread out over a larger volume. However, the energy density of the vacuum remains constant. A cubic meter of space today has the same amount of vacuum energy as a cubic meter of space a billion years ago. This means that as space expands, more space is created, and therefore more dark energy comes into being. This creates a positive feedback loop. Expansion creates more dark energy, which in turn causes more expansion. For the first 8 billion years of cosmic history, the universe was smaller and the density of matter was high enough that gravity was the dominant force, and the expansion was indeed slowing down. But as the universe continued to expand and matter thinned out, the relentless, constant push of dark energy eventually took over. About 5 billion years ago, the universe passed a tipping point and began its current era of accelerated expansion. This model, known as lambda CDM, lambda-cold dark matter, is the standard model of cosmology today. It beautifully fits all the data we have from supernovae to the CMB. But it comes with its own deep problems. One is the fine-tuning problem. When physicists try to calculate the expected energy of the vacuum from quantum theory, the result is catastrophically wrong. It's about 120 orders of magnitude larger than what we observe. This is the single worst prediction in the history of physics. Another is the coincidence problem. Why are we living in the specific cosmic epoch when the density of matter and the density of dark energy are of the same rough order of magnitude? It seems like an incredible coincidence. These puzzles have led to other speculative ideas. Perhaps dark energy isn't a constant, but a dynamic field that changes over time, dubbed quintessence. Or perhaps our theory of gravity itself is wrong on cosmic scales, and there is no dark energy at all, just a misunderstanding of how spacetime works. For now, however, the evidence points toward a universe dominated by this strange energy of the void. When we finally complete our cosmic census, the results are humbling. The inventory of the universe's energy density is 68% dark energy, 27% dark matter, 5% ordinary matter, the stuff of stars, planets, and people. This is the modern picture of our universe. A staggering 95% of reality is composed of substances we do not understand and cannot directly see. We are strangers in our own cosmos. Our quest to understand the expansion of the universe has led us to a place of profound mystery. We started with the visible, with the light from stars and galaxies, but the behavior of that light has forced us to accept that the true story of the cosmos is written in invisible ink. We have discovered that the majestic structures of the universe, the great walls and filaments of the cosmic web, are built upon a hidden scaffolding of dark matter. Without its gravitational influence, we would not be here. We have also discovered that the ultimate fate of our universe is not being decided by the matter we can see, but by an even more mysterious force, dark energy, which is accelerating the expansion and pushing galaxies apart with ever-increasing speed. Our situation is like that of ancient mariners mapping the world. They could chart the coastlines and observe the effects of winds and currents, but they had no knowledge of the tectonic plates moving beneath the waves or the convection in the Earth's mantle driving it all. Similarly, we can map the visible universe, but we are now aware that its structure and destiny are governed by vast, unseen continents and currents in the cosmic ocean. The discovery of dark matter and dark energy has not been an end to a story, but the beginning of a new one. It has opened up fundamental questions that will drive physics for the next century. What are these dark components? Do they interact with each other? Will dark energy remain constant, or could it change in the future, leading to an even more dramatic end for our universe? This new picture of the cosmos sets the stage for our final inquiry. Knowing the ingredients, what can we say about the future? What are the possible fates of a universe dominated by the dark? This will be the subject of our final article, where we will journey to the end of time and explore the ultimate destiny of everything. The end of everything, the ultimate fate of the cosmos. We have traveled to the edge of perception and back. Our journey began with a simple question that shattered our intuition. What is the universe expanding into? This led us to the revelation of a self-contained, self-creating reality woven from the fabric of spacetime. We then became cosmic archaeologists, deciphering the ancient light of the cosmic microwave background and the stretched song of redshift to find irrefutable proof of our expanding origins. Finally, we ventured into the shadows, confronting the unseen architects of our universe, the gravitational scaffolding of dark matter and the relentless, repulsive force of dark energy. We arrive now at the final frontier, armed with a humbling inventory of reality. A cosmos where 95% is unknown, and where an anti-gravitational energy of the void holds sway. We have traced our story from the beginning, but every story must have an end. And so, we face the most existential question of all. Where is this all going? If the Big Bang was the opening chapter, what is the final page? If the universe had a birth, must it also have a death? This final article is a journey to the end of time. It is an exploration of eschatology, not the study of mythical prophecy, but of cosmic destiny, written in the language of physics. We will weigh the forces of gravity and dark energy in a final cosmic tug-of-war to determine the fate of all existence. We will explore the three great theoretical endings: a fiery collapse, a violent tearing apart, or a slow, silent fade into darkness. Finally, we will dare to ask what might lie beyond the end. Is death the final word, or could our universe be part of an eternal cycle of creation and destruction, a single bubble in an infinite bubbling multiverse? This is the ultimate story, the story of the end of everything. And in contemplating this end, we may just find the true meaning of our own brief, brilliant moment in the cosmic day. The ultimate fate of the universe hinges on a delicate balance of power between two cosmic titans. On one side is gravity, the collective pull of all matter, both normal and dark, always trying to pull everything back together. On the other side is dark energy, the intrinsic energy of space, always pushing everything apart. The future depends entirely on the nature and strength of dark energy. Based on what we currently know, there are three primary scenarios for how the story could end. For much of the 20th century, this was considered a leading possibility. The Big Crunch is the gravity wins scenario. It imagines a future where the pull of matter is ultimately strong enough to overcome the cosmic expansion. Or perhaps dark energy is not a constant, but a force that weakens over time. In this scenario, the expansion of the universe would slow down, grind to a halt, and then reverse. The redshift of distant galaxies would turn into a universal blue shift as everything begins rushing back toward everything else. The cosmic film would play in reverse. Galaxies, once isolated islands, would begin to merge. As space contracts, the temperature of the universe, including the cosmic microwave background, would start to rise dramatically. The sky would become brighter than the surface of the sun, everywhere at once. Stars would be vaporized by the ambient heat. Planets would be torn from their orbits and incinerated. As the contraction accelerates, atomic nuclei would be ripped apart into a soup of elementary particles. In the final moments, space and time themselves would lose all meaning as the entire universe collapses back into an infinitely hot, infinitely dense singularity, a mirror image of the Big Bang. It's a dramatic and symmetrical end. However, given our 1998 discovery that the expansion is accelerating, not decelerating, the Big Crunch is now considered highly unlikely, unless the nature of dark energy changes dramatically in the future. What if dark energy is even more powerful than we think? The standard model assumes dark energy is a cosmological constant. Its density remains the same as space expands. But what if dark energy is something more volatile, a form of phantom energy, whose density increases as the universe expands? If this were true, it would lead to the most violent end imaginable, the Big Rip. In this scenario, the accelerating expansion would become runaway. The repulsive force of dark energy would grow stronger and stronger over time, until it could overcome all other forces in nature. The destruction would happen in stages, from the largest scales to the smallest. First, billions of years from now, the ever-increasing push would become strong enough to overcome the gravity holding superclusters of galaxies together. Then, the clusters themselves would be unbound. A few 100 million years before the end, the force would be strong enough to overcome the gravity holding individual galaxies together. The Milky Way would be torn apart, its stars flung into the rapidly expanding void. As the end approaches, the process accelerates catastrophically. A few months before the end, planetary systems would be destroyed, with the Earth ripped away from the Sun. In the final minutes, the Sun and the Earth themselves would be obliterated. In the last tiny fraction of a second, the electromagnetic force holding atoms together would be overwhelmed, and they would be torn apart. Finally, even atomic nuclei would be ripped asunder by the infinite force of dark energy. The very fabric of spacetime would be torn to shreds. The universe would end not with a whimper, but with a cataclysmic rip, where every single particle is isolated from every other, unable to interact, in an infinitely large void. It is a terrifying and complete annihilation of all structure. This is the scenario that is most consistent with our current observations. It assumes that dark energy is a cosmological constant and will continue to drive a steady, eternal acceleration. This ending is not fiery or violent, but it is perhaps the most profound and melancholic. It is a story of a slow, inexorable fade into cold, empty darkness. The journey to the heat death unfolds over timescales so vast they defy human comprehension. In about 100 billion years, the The accelerating expansion will have pushed all galaxies outside our local group, the cluster containing the Milky Way and Andromeda, beyond our cosmic horizon. From our vantage point, the night sky will become almost completely empty, save for the aging stars of our own merged galaxy, Milkomeda. To any future inhabitants, the universe will appear static and lonely, with no evidence of the Big Bang or other galaxies ever having existed. In about 1 to 100 trillion years, the era of star formation will end. All the available gas will have been used up. The last, smallest red dwarf stars will finally exhaust their fuel and flicker out, leaving behind a universe populated only by stellar remnants. Black dwarfs, neutron stars, and black holes. The universe will enter its degenerate era, a realm of cold, dead objects. From 10 to the power of 30 to 10 to the power of 100 years. Over almost unimaginable timescales, even these remnants will decay. Galaxies will dissolve as planetary systems are disrupted and stellar corpses are ejected into the void. According to some theories, protons themselves may decay, causing all normal matter to disintegrate into a bath of light and other particles. The only organized structures left will be black holes. Beyond 10 to the power of 100 years. This is the black hole era. But even black holes are not eternal. Stephen Hawking showed that they slowly evaporate by emitting Hawking radiation. A stellar mass black hole will take about 10 to the power of 67 years to disappear. The supermassive black holes at the centers of galaxies will take a staggering 10 to the power of 100 years. As the last and largest black hole evaporates in a final, faint flash of light, the universe will enter its final state. This is the heat death. The universe will be a near-perfect vacuum, unimaginably vast, cold, and dark. It will be a thin, featureless soup of photons, neutrinos, and other elementary particles, drifting ever farther apart. All structure, all information, all complexity will be gone. The universe will have reached a state of maximum entropy, perfect equilibrium. And because time itself is linked to change, the arrow of time is defined by increasing entropy. In a universe where nothing happens, time itself may lose its meaning. It will be a quiet, cold, eternal end. Let us try to imagine this final state. It is a canvas of pure black, stretched to near infinite proportions. The temperature is infinitesimally close to absolute zero. The brilliant fires of creation, the dance of galaxies, the birth and death of stars, all are but a forgotten memory, a fleeting dream that ended trillions upon trillions of eons ago. There are no clocks to tick, for there is no change to measure. There is no here or there in any meaningful sense, for the distances between the few remaining particles are so vast that they will likely never interact again. The expansion that once drove the cosmic story has rendered the stage so large that the actors are forever lost to one another. This is the triumph of the second law of thermodynamics on a cosmic scale. The law states that in a closed system, entropy, disorder, always increases. The universe, in its final state, will have achieved perfect disorder. All the useful energy that once powered stars and life will have dissipated into useless, uniform, low-grade heat. The cosmic story, which began with the perfect order and low entropy of the Big Bang, will end in the perfect disorder and high entropy of the heat death. It is a humbling and perhaps unsettling vision. It suggests that everything we see, everything we build, every piece of art, every act of love, is ultimately destined to dissolve into the cold void. The universe, it seems, is a magnificent but temporary performance. Is the heat death truly the final word? Or could our human perspective, still tethered to a single cosmic event, be too limited? On the speculative fringes of theoretical physics, ideas exist that challenge the finality of this end. One such idea is the cyclic universe. What if the Big Crunch were to happen, but instead of ending in a singularity, the universe bounces? Perhaps some unknown quantum gravity effect would cause the collapsing universe to rebound into a new Big Bang, starting a new cycle of expansion and contraction. In this eternal cosmic dance, our universe would be just one in an infinite series of universes, each born from the ashes of the one before. A more popular idea in modern cosmology is eternal inflation and the multiverse. This theory suggests that the superfast expansion in the first moments after the Big Bang, known as inflation, may not have stopped everywhere. Perhaps it is still ongoing in the vast superspace beyond our observable universe. In this view, our universe is just one bubble that nucleated when inflation stopped in our local region. But outside our bubble, other bubbles are constantly forming, each giving birth to a new universe, possibly with different physical laws and constants. This creates a multiverse, an infinite foam of bubble universes, constantly being born from an eternally inflating sea. If this is true, then the story of our universe may have an end, but the story of creation does not. The death of our universe in a cold freeze would be a local event, insignificant in the context of an infinite multiverse where new Big Bangs are happening all the time. Our universe's end would not be the end, but merely an end. These ideas are currently untestable and lie in the realm of mathematical speculation. But they offer a profound alternative to a single, final death. They suggest that existence itself may be eternal, even if our particular corner of it is not. We have come to the end of our journey. We began with a simple question about space and ended by contemplating the death of time itself. We have learned that we live in a universe whose fundamental nature is expansion, whose primary constituents are a mystery, and whose most likely fate is a slow, cold descent into nothingness. Faced with this cosmic panorama, it is easy to feel a sense of insignificance, a cosmic pessimism. If the entire universe is temporary, what meaning can our tiny, fleeting lives possibly have? Perhaps the meaning lies not in permanence, but in the miracle of the present moment. The universe, for 13.8 billion years, has been expanding, cooling, and structuring itself. Through a chain of events guided by the laws of physics and sheer chance, on at least one small planet orbiting one ordinary star, the universe has produced beings capable of looking back upon it. We are, in the poetic words of Carl Sagan, the universe's way of knowing itself. The atoms in our brains were forged in the hearts of dying stars. The laws that govern our bodies are the same laws that shape the orbits of galaxies. We are not separate from the universe. We are an emergent property of it. Our consciousness is a brief flicker of light in the vast cosmic darkness, but in that flicker, the universe becomes aware of its own grandeur, its own beauty, and its own impending doom. The heat death may be the ultimate fate, but it lies in a future so distant it is functionally infinite. What matters is the here and now. What matters is that we, for a brief moment, have the privilege of existing, of wondering, of loving, and of understanding. The meaning of our existence is not erased by the universe's end. It is made infinitely more precious by it. Our quest for knowledge, the very journey we have just taken, is our rebellion against the silent void. To ask why, in a universe that may have no ultimate purpose, is perhaps the most human and most noble act of all. The story of the cosmos is the greatest story ever told, and for a short while we are here to listen, to learn, and to add our own small verse to its endless song. And that, in itself, is a meaning grand enough for any universe.